Okay, so we start with the trajectory transfer. So, as you know, once the satellite has to be injected into the orbit, so the precise performance of the rocket it is not possible. The rocket will never perform the things that you desire, okay, because of the unknown wind conditions and various other factors which contribute to the performance of the rocket. Okay, say if you want to put the satellite in geostationary orbit or the low earth orbit. So, in both the cases you need to maybe put in the some elliptical orbit or maybe in some circular orbit, okay, and the rocket where it injects. So, the amount of the velocity vector which is required in that point where the rocket is injecting. So, at that point itself may not be coinciding with the orbit which is required, and the velocity vector also may be much off what is than what is required in the desired orbit, and therefore, the orbit correction is required. So, this orbit correction, so naturally the question arises how to do it, but the idea here is the in whichever path the satellite is moving, that path must be corrected. Okay. So, correcting that path means moving the satellite from one trajectory. So, that is the present path in which the satellite is moving to another trajectory, and therefore, this terminology it is called the trajectory transfer. So, we start with this trajectory transfer and see into why uh, how to what are the various regions which are which go into the design of the trajectory transfer, and what are the regions which control this trajectory transfer. Okay. So, to start with trajectory transfer, is defined as the change in the orbit through change in velocity vector usually by the application of impulse. Okay. So, often one or more impulses will be required to complete the trajectory transfer. So, let us consider a very small case. Say this is the earth, and by firing the rocket you have placed certain satellite in the orbit. So, the orbit of the satellite it looks like at the present moment. Okay. So, satellite is often injected at a low altitude. So, say this satellite has been injected at the perigee position. So, why at low altitude? Because taking at a higher altitude. So, you will in the rocket you will have the satellite inside kept. This is your satellite. Okay. So, if you want to carry along with this satellite, so this rocket itself will have some propellant mass. Okay, let us say this is the last stage of the rocket which we are going to discuss toward the end of this course. So, this is little off the track, but just I am introducing it for your convenience. So, let us say this is the third stage. Okay. So, in the third stage besides satellite you have this unnecessary weight involved with the satellite, which is the structural weight of the rocket, and beside the fuel is also there. So, all these weights are together. Now, if you want to take it to a further height along with this rocket. So, what will happen that you have to spend fuel for this extra structure which is coming because of the presence of the rocket. Okay. So, you are going to lose energy. Okay. Therefore, your propellant mass required will be much more, and if you inject the satellite at a smaller altitude with high velocity. So, what will happen here? So, your rocket is gone, this part is taken off, okay, and only the satellite is remaining. So, in the satellite then you have the propellant system, the propulsion system is present. So, this satellite itself has certain storage of the fuel. Okay. So, using this propellant, so satellite can then be boosted from the present trajectory to a new trajectory. So, you can see that in this case you have the lower mass involved, while in this case the larger mass involved. So, this saves a lot of energy. Now, if you have injected the satellite suppose here in this place, okay, and your required orbit is this one. Okay. So, therefore, you are much off the desired orbit. This is the desired orbit and this is the present orbit, and therefore, you need to boost, say this is called the perigee. Okay. So, you need to boost the perigee, or this is also called the raising of the perigee, and once you raise the perigee and the velocity in while raising the perigee it matches with this circular orbit, then the satellite will really follow this course. Okay. So, this way you can precisely control the position and velocity of the satellite, and therefore, you can put it in a desired orbit what is really required. Okay. So, with the rocket obviously, it is not possible exactly to do this thing, because here the you can give impulses little. So, in the course of time you can bring it here in this place, okay. Or maybe one impulse, suppose here I need to raise the perigee. So, what I will do here, I will give the impulse. So, as I give the impulse here at the apogee position. So, this will make it here nothing will change. Okay. So, here this distance will not change, only thing now the velocity will be higher, and therefore, this satellite will go into this orbit, and but the perigee change will take place and perigee will rise to this point. Okay. So, by doing this you can raise the perigee. Okay. So, how much correction is required, it depends on the situation at hand. Okay. So, the situation that I have presented here, this is also called the geosynchronous transfer orbit. Let us say this is the geosynchronous orbit. Geosynchronous orbit. Okay. So, this is geosynchronous or maybe the geostationary orbit. So, once you are launching the satellite, so you are leaving the satellite here and satellite is performing like this, and it is possible that the apogee also does not match with this place. Okay. Rather the apogee has gone like this. Okay. You have put the satellite such that it is in an elliptical orbit. Therefore, in that case you need to raise this apogee also and raise this perigee also, and this GTO, this is called the geosynchronous transfer orbit. So, actually you place the satellite here in this place and thereafter you bring it to the right condition. So, doing this kind of trajectory transfer, it is a part of our study here. Okay. So, next 9 to 10 lectures we are going to devote on this. So, various kind of trajectory transfer, how to do it, when the energy involved is minimized, and sometimes maybe the small eccentricity you require while transferring. Various factors are there. In fact, sometimes it may be that you catch the satellite you have to transfer it such that you have to catch the satellite in another orbit. So, that is called the chase maneuver. So, and that is mostly in the case of say the if you have to hit a satellite with a missile. So, during that time the maneuver you will do, that will be called the chase maneuver, or either the rendezvous problem, in which one satellite is already in the orbit, another satellite is in different orbit, and you want to do the rendezvous of these two satellites. That is, you want to approach one the second satellite, say in this case one satellite is moving here, and you have injected just a satellite here in this orbit, or the already in a orbit the satellite is moving like this, and you have to catch up with this. So, what strategy you plan, so that you catch up with this one. So, all these are part of this trajectory transfer maneuver, and it is a very interesting topic in fact. So, in trajectory transfer, so many times it is required that satellite may be put in a temporary orbit. And this may be quite necessary from the point of view that while you are launching the satellite. So, at the time of ejection from the rocket, okay, while you are injecting it in the orbit. So, at that time it goes under severe conditions. So, after that, after the injection, then you may be able to, you have then the time to check its various components, okay, how the system is performing, and thereafter you really put in the desired orbit. So, this is required from the point of view of a temporary orbit, which may be necessary say the logistic point of view. The logistic convenience, and then maybe the further maneuver required. So, already we have discussed why this satellite trajectory transfer is required. Okay. So, the first this trajectory transfer might have been done. Okay. The first satellite maneuver or trajectory transfer most likely occurred on January 2nd, 1952. This is 1959, because this was done for Luna, okay, not 52. So, Soviet satellite Luna 1, which was sent to moon in it was launched on January 2, 1959. Okay, this, so maneuvering was done for this lunar satellite to send it to moon, but it missed the moon. Okay, it missed the moon and was lost in space. So, if you look into this before that, because the why I am telling here the most likely, because the whole history is not available. In those days the things were done very secretly. So, exactly the dates and other things it is not very available in a very confirmed way, but it is most likely on the January 2, 1959, and once the Luna was sent to the moon in this this was a race between the US and Russia basically. So, both the countries were trying to send their satellite to the moon first. So, then Soviet Rus was the first to do this operation. So, thereafter America it rushed up to this business. Okay. So, the Luna was once the Luna was sent to that. So, what happened that this missing that the satellite is not reaching the moon, it happens because suppose this is the moon, okay, and you are sending the satellite in a trajectory. So, if the velocity required to be captured by this moon is higher than that required, but suppose the velocity required to be captured in this moon orbit, okay, v, this is the v required, okay, and if your velocity at present, this is the v present, is greater than v required. Okay. So, simply it will not go into this orbit, but it will just escape in this space. So, it will take, there will be trajectory turn, but it will not go into this orbit and it will escape in the space, and therefore, it is a lost forever. Okay. And of course, you know that satellites are, once you send the satellite to such a large distance. So, it is not loaded with so much of fuel that you can bring it back into the desired trajectory. So, these maneuvers are managed very precisely. So, you know about the Chandrayaan, the India has done this Chandrayaan mission. So, for the Chandrayaan mission, this suppose this is the earth and this is the moon. So, moon is moving around the earth in this orbit. Okay. So, what was required that the satellite which was first launched in a orbit, which was a elliptical orbit. Okay. Here this distance is very exaggerated. Actually, this distance we know that the distance between the moon and the earth is 3,38,440 kilometers. Means 3,84,400 kilometers. Okay. So, this distance is very large, which we cannot show here. So, what was done? It was put in a temporary orbit here. Okay. Now, this initially this perigee position was around 255 kilometers. Okay, approximately the exact values it is not known to me, but prior to this launch review which I did, in that it was shown that this is going to be launched around this position. So, taking this position to be 255 kilometers to 300 kilometers. Okay. So, thereafter the apogee was boosted. Okay. So, slowly this distance was increased. So, now we can show it here. Say this is the earth and here is the moon. In the satellite you have launched, it is moving in this orbit. So, in this maneuver the apogee was boosted and also the perigee was raised. Okay. So, whatever the, suppose the perigee is here at 255 kilometers. Okay. So, this was also raised. Why this is required? Because you know that the atmosphere is present. So, near the earth surface, So, there is at even at 255 kilometers enough atmosphere is there to kill the kinetic energy of the satellite, okay. And therefore, this was also boosted and this helped in. So, if you once you have boosted here, so you lose lesser energy because of the aerodynamic drag. So, once this is boosted, the perigee is raised and you keep on raising the apogee also. So, the apogee can be brought from here and then it can be brought here into this place. Okay. So, it was kept raising until unless it reached a boundary. Okay. So, this is called the sphere of influence. Okay. So, let me make this boundary. Say this is the sphere of influence of the earth and this is the sphere of influence of the moon. So, after this distance the moon gravitational force will be more dominated and here the gravitational force of earth is more dominating. So, once it reached here, so there was a window of 2 minutes. Okay. So, this was told that this was around 50 kilometers, 50 kilometers as far as I remember. So, let us say this was a very short period if we take in terms of time. Okay. So, only a period of 2 minutes was available. So, during that period the satellite was to be injected into the domain of the moon, the sphere of influence of the moon. Okay. And once you are injecting the satellite into this domain, so what is required also that the velocity should not be higher. If the velocity is higher, suppose here you want to put it in this orbit. Okay. So, if this is a circular orbit, so there is something some velocity is required to move in this orbit, and if you exceed this velocity, then what will happen? So, simply the satellite will enter the domain of the moon, but it will go outside this. It will not come in the orbit around the moon, and therefore, it will be lost forever, and that kind of orbit it is called the hyperbolic orbit, where the satellite will go beyond your reach, it will not be captured by the moon. So, in this small window the satellite was to be captured. So, if the satellite was moving like this, so here now the satellite is moving. So, then it must be deboosted here, so that it gets captured by this moon. Okay. So, you raise the perigee and simultaneously you have to deboost the velocity of the satellite, so that the moon captures it. Okay. So, doing all these operations, it is a complicated operation and it has to be done in a very precise manner and doing orbit determination each and every time. So, orbit determination we have already done, but those kind of the orbit determination problem we did. So, there you required the exact values of the position and the velocity, that is the position and velocity coordinates are required. Then you can find out in which orbit it is moving, where its location is with respect to the earth and with respect to the moon. But in fact, these measurements are always faulty, and therefore, we need some extra estimation or do more data processing to find out in which orbit it is moving. So, that data processing it can be done using either the Kalman filter, the extended Kalman filter, or using the batch processing method. So, those are beyond the scope of this course. Okay. But in fact, this is required. So, the orbit determination was simultaneously being done, and once the things were observed that now it is in this position, all the proper maneuvers were done to put the satellite around the moon. So, this is one way of doing it, that you are raising the perigee continuously. Another way of doing the same thing can be this is your earth, okay, and here is the moon. Okay. So, you have placed the satellite in an elliptical orbit, okay, and you want to capture it around the moon. So, you can give impulse in this orbit and it can be brought like this, and thereafter it can be captured. Okay. So, another possibility is doing this. So, various kind of trajectory transfer it is possible, and it depends on how much confidence you have in the maneuver. If you have done this kind of maneuver already, then it is easy to do it. If you have not done, so this kind of maneuver, in fact, the ISRO has done for transfer from the GTO to the geostationary orbit. So, geotransfer orbit, from the geotransfer orbit to geosynchronous orbit, the satellites were already raised using this method, and so it was very easy for them, and in fact, this technologies were mastered. So, the foolproof method were utilized for doing this trajectory transfer. Okay. So, the first satellite maneuver, probably it was done on 2nd of January 1959, and that was done for the Luna 1 satellite. So, the Luna 1 missed the moon by 6,000 kilometers. Again on September 12, 1959, Luna 2 was maneuvered. So, after correcting the difficulties which were faced in the Luna 1, so Luna 2 was tried out. So, this Luna 2 was captured by the moon, but then what happened, that it crashed into moon. This crashing was not incidental, but it was meant. Okay. This crashing was meant. So, what is the reason that this crashing was meant? So, reason was that at that time the satellite, this propulsion technology, the retro rockets were not in developed stage. Retro rockets means once you are you want to keep the satellite, if you want to land the satellite on the surface of the moon, then what you require, that while landing, if the something is landing on the surface of the moon. So, slowly it has to be brought to the surface of the moon. So, while landing, the retro rocket must be fired to support the weight of the satellite, okay, so that it lands smoothly on the surface, otherwise it will crash and it will get destroyed. Okay. So, this retro rocket technology was not there, and therefore, this crash was meant for already, that this is going to happen. Okay. So, later on the soft landing technologies were developed. Okay, now, the question arises that we are putting the satellite in a parking orbit or a temporary orbit. So, this kind of temporary orbit, it may be useful from various point of view. So, the why we go for parking orbit. So, greater reliability, because the satellite undergoes severe launching and injection conditions. This is injection on the in the orbit. Therefore, further checks must be done before any maneuver is carried out. Okay. Parking orbit may also be used for the photography. Okay. You want to take a close photography of the things on the earth, okay, for some military secrets. Already for the military, the spy satellites are there, which are put on small altitude, thereby the photographs can be taken, which will have higher resolution, and even the using satellites, the movement of the troops, or so you have the satellites of say the resolution 1 meter. So, any object of 1 meter can be seen very easily using the satellites if the satellite is placed on the lower altitude. So, the parking orbit, in that case it becomes very important that if the satellite is at the lower altitude, you do the necessary operation, and thereafter you can raise to the higher orbit. Okay, saving fuel. So, again there may be some unnecessary components, so that you can reject, and whatever is required, that you can send it to the higher orbit. So, in the case of the the Apollo satellites, so there were two models, the command modules and the lunar module. So, the command module, while it was placed in the parking orbit around the earth, so the command module was kept there and the lunar module was sent to the moon. So, this way you save a lot of fuel, because sending a larger mass to moon means you are going to spend more fuel, and your then the satellite also, the lunar model that you are going to send it to the moon, that also requires a large amount of fuel. Size increases, cost increases, complication increases, so many things that happen simultaneously. Now, the classification of the trajectory, the trajectory transfer we do, it can be done based on various factors. So, the first we decide on the basis of center of force, based on the center of force. So, here we can have transfer between orbits with same center of force, transfer between orbits with different center of force. Okay. So, in the with the same center of force, this you have already seen as the example that that is from the geo transfer orbit to geosynchronous orbit once the satellite is raised, and this transfer between the orbits with different center of force is an example where the satellite is transferred from the earth orbit to the moon orbit, or maybe from earth orbit to the Mars, and wherever it is possible. You can send it you can send the satellite anywhere in the solar system. Okay, but obviously it is going to take a lot of time. The second categorization can be done based on the number of impulses. So, we can have single impulse transfer. This is of course, the minimum possible. then 2 impulse, three impulse, continuous thrust transfer. Of course, these three are frequently used. Okay, besides we have besides the above two categorization, we can also do the categorization based on the plane of transfer. So, we can say this is the based on plane of transfer. So, in this category will fall the coplanar maneuver, so you are doing the maneuver in the same plane, okay, non coplanar maneuver and the combined maneuver. Okay, so these are the broad category in which the trajectory transfers are put. So, here while going through the trajectory transfer, we will do the coplanar maneuver, we will also do the non coplanar maneuver, and the combined one is obviously the combination of these two. So, the coplanar maneuver. So, what we do? We start with this coplanar maneuver, and under this then you will have the single impulse transfer, 2 impulse transfer, 3 impulse or the continuous transfer. Okay. And this is based on the center of the force. So, obviously, if the transfer case with different center of force, this we are not going to do. Okay. But this we will cover in this course, the transfer between the orbit with the same center of force. So, in the coplanar maneuver, what are the things which can be affected? So, the coplanar maneuver with same center of So, what are the things that you can effect in the coplanar maneuver? So, the things that can be affected semi major X, eccentricity and the argument of PTG. These are the things that you can do changes you can do in the coplanar maneuver. So, these are the 3 parameters of the orbit, and the rest other 3 parameters are these are the 3 parameters, and the rest other 3 parameters are the inclination of the orbit, nodal angle which is capital omega, and then of course, this theta. Theta is the which you call as the true anomaly. Okay, so theta is basically it comes under this one only, in the coplanar maneuver itself. So, we let us reject it. These are the two things which change the plane of orbit, change the plane of orbit, and therefore, they do not fall in under the category of coplanar maneuver. Now, the coplanar maneuver, it can be categorized as, so the coplanar burn, this can be categorized as the tangential burn and the non-tangential burn. So, what does it imply? Say this is the center of the force and your satellite is moving in this orbit, this is r initial, and you want to send it in a higher orbit, this is the radius r f. So, you can do this by various ways. So, basically this is a coplanar maneuver that we require here in this case, because both the orbits we are assuming they are in the same plane. So, I can do the tangential burn, means I give impulses here in this place, I burn the rocket I fire the rocket in this position, and therefore, I can give a tangential burn or delta v is imparted in this direction. So, once you impart the impulse or you change the velocity in this direction tangent to the trajectory. Okay. So, satellite will move away from here to here. If the delta v is appropriate, then it will go from this orbit to this orbit in an elliptical orbit. So, it is a moving around like this now. Now, again you have to send the satellite. Now, this is in an elliptical orbit, and if you want to send it in this orbit. So, you need to further boost it in this position. So, you need to give delta v impulse. So, this is delta v I and this is delta v f. Okay. So, you give an impulse of the required magnitude such that it goes into this orbit, and this fine tuning can be done here to put it in the exact orbit. So, this is called the tangential burn, because in every place we are giving the impulse tangential to the trajectory or along the velocity direction itself. Okay. In the non-tangential burn, again this is the center of the force, satellite is moving in this orbit, okay, and I need to put it in a higher orbit. Okay. So, it is possible that I can give an impulse here in this place. So, here suppose this is your velocity vector v circular in the initial orbit, okay, and I can send it along any of the trajectory. I can send it like this, okay, or either I can send it in this orbit, I can send it here this way, various possibilities are there. So, if this v I see, this is the initial velocity in this circular orbit, okay, and I am sending the satellite suppose along this trajectory. Okay. So, here v elliptical, this is the elliptical orbit, then you are sending. So, the satellite will move along this orbit, it will be something like this. Okay. A crude representation I am giving you here. Okay. Of course, if the earth is larger, so we cannot show it like this, because of in many cases you will see that the earth is almost your satellite is at the altitude of 300 kilometers even, and in the geostationary orbit the altitude is around, the radius of the orbit is around 42,000 kilometers. So, we have to check for all that while the perigee does not touch the it does not touch the earth, or not touching the earth only is not the requirement, but it should not come in the atmosphere also, otherwise it will get burned. Okay, so, this care must be taken care of. So, once you are giving the impulse here in this place, so what is the change in the velocity required? So, this is the final velocity vector here at this point, and this is the initial velocity vector. So, the change will be done along this line. Okay. So, this is the delta V I initial required, okay. Delta V I initial impulse required to put it in this orbit. Okay. And once it reaches here, so it is going in this orbit along this direction, while your velocity vector in this orbit is along this direction, and therefore, you must give another impulse delta V f in this place, so that it comes in this orbit. Okay. But if you do this kind of maneuver, so it is not necessary that all of them obviously here if you do the if you give the impulse here in this place. So, the amount of energy that is required to send it in this orbit, and then thereafter you give one impulse here in this place to place it in this orbit. So, the both the energies can be combined, or the both the impulses can be combined, how much impulse is required. Okay. And here also you can do the same kind of calculation, how much impulse is required here and how much impulse is required here in this place to put it in this orbit. In doing this kind of burn, okay, so energy becomes very important factor, because you do not want to spend large amount of energy. So, you would like to do efficient fuel management. Okay. You would like to do the minimum expense of the propellant, okay, such that you can keep the satellite in the orbit for a longer time. If the propellant is lost, if the propellant is not there, then later on you cannot change the orbit of the satellite. Okay. Over a period of time, the satellite orbit drifts. Okay. In the low earth orbit, because of the J2 component of the earth gravity, okay, which is due to the J2 gravity, it comes into the picture because of the non-sphericity of the earth. So, it rotates the orbit of the satellite. So, if the say the orbit of the satellite is like this. So, because of J2 it will turn like this, okay. And also there are various things involved, like the not only the inclination, but your orbit also rotates like this, the nodal angle also changes. Okay. So, all these various factors are there, because of the aerodynamic drag, then your semi major axis will change. So, all these things are to be taken into account. So, if your energy spent is large, means you are going to lose all your propellant, and the life of the satellite will simply go down. So, keeping the life of the satellite large, that is keeping your satellite for a longer period, you need to do the efficient fuel management. So, every maneuver has to be optimized such that the fuel loss is minimum. To find out for a given amount of impulse, what will be the change in kinetic energy. So, let us assume this is our V initial velocity, and the amount of impulse which is available is delta V, and delta V we apply at certain angle delta here. So, this is our V f, the final velocity, okay, and this is the delta V applied. So, what will be the change in kinetic energy? So, change in kinetic energy will be given as delta k E 1 by 2 V f square. This is kinetic energy change per unit mass minus V I square, and this we need to find out for a given amount of impulse. So, now this impulse can be given along this direction, along this direction, or along this direction, along this direction, or whatever the direction we have chosen right now. Okay. So, or either opposite to this, but in what situation, for what value of this delta, this change in kinetic energy is going to be maximum. Okay. So, this V f can be written in terms of this angle theta. So, V f, let us write here in this place, V f square, this is equal to V I square plus delta V f square, okay, minus 2 V I times delta V f cos theta. Okay. And if we replace theta in terms of delta, or either we can work with the theta itself here and write it. So, this becomes 1 by 2 V I square plus delta V f square minus 2 V I times delta V f cos theta minus V I square. Okay. So, this cancels out, and what we get here, delta V f square 1 by 2 minus V I times delta V f cos theta. Now, you can see from this place that the change in kinetic energy depends on this term, because delta V f, anyhow the delta V f magnitude V is fixed. We are taking this for a fixed amount of impulse. So, if theta equal to theta is more than 90 degree, okay. So, this quantity is going to be positive. So, if you have theta equal to 180 degree, at that time delta will be equal to 0 degree. So, then you will have this quantity as delta V f square plus V I times delta V f, and this is the maximum amount of change in kinetic energy that you can register. You cannot exceed this value, okay, for a given amount of impulse. So, we will continue next time with this discussion. Thank you very much.